plus, like how would it just be us in that sequence?
Yeah, so I wouldn't do that. I would do something more like what you did on your homework. Yeah. Like on your homework where you did odds and integers or z and 3z, stuff like that, where you can actually come up with a function instead of like a mapping where you have to draw it. Okay. I don't know what I'm doing. We're going to get a blank page. If y'all want your homeworks back, I'm going to look at that one that Jacob was talking about. Does anybody want their homework back? Maybe after you see it. Do you want to look at your homework while we go through this one? Y'all are not answering me, but it's fine. I'll just hand them to you. You don't want it? You feel good about it? Okay. Yes. Were you joking? Were you not being serious?
Was I being serious?
I think you should. I mean, I can, but I think maybe you should. Maybe I'll do it. You can talk me through it, but I'll write. How about that? Okay. So I think it's a notation problem more than a what proof by induction is problem, right?
Yeah.
So the summation from I equals 1 to k, or n, of 2I is n squared plus n. So for the base case stuff, you just do, to 1 to I. This is 2 times 1, which is 2. And 1 squared plus 1 is 2. 2 equals 2. Check. For the inductive hypothesis, I'm sorry, Corey, I told you could talk, and I'm just doing all the talking. You are looking at the summation from I equals 1 to k of 2I is equal to k squared plus k. So this is like this, And what we want to show is that the summation from I equals 1 to k plus 1 of 2I is k squared plus k. All right, so what I'm going to do is set that up with I equals 1 to k plus 1 of 2I. This sum is the first k plus 1 terms. So I'm going to split this into the first k terms and the k plus first term. You don't have to write, I think what I did in class and maybe made this confusing is that I went ahead and plugged in k plus 1 to the thing, so I didn't write the summation. But because it's not a summation anymore, it's just the one term, it's just the k plus first term. So the summation from I equals 1 to k plus 1 splits into the sum from 1 to k plus the k plus first piece. So it splits into this, and then this thing you use the inductive hypothesis for. So this is k squared plus k, and then this is 2 times k plus 1. And then you've got to make this look like, I messed this up right here, folks. Thank you. This should look like this. I'm so sorry. That's where we're headed, so we got to work with this to make it look like that. A lot of people really don't like the summation notation, and in the past I have done a thing where like I'll do, instead of writing the sum from I equals 1 to k of 2 times I would just write 2 plus 4 plus 6 plus ... plus 2 times k, and that is the same thing as this. So you can plug in the first couple of things to see what the pattern is and just write it out like long instead of writing it in the summation notation. It was like, no, we can't. You don't like this?
I like the summation.
Yeah. This is the sum of the first k even integers. 2I is the sum of the first k even integers, right? All right. Other questions or comments about that? Jacob, does that help? I think in class when we, oh my Lord, in class when we did this, um, I just wrote this. I didn't write this step. I just put this right there. And I think that probably was confusing. I'm sorry. Okay. Corey, I didn't let you talk at all. I don't know what happened. Okay. Do we think we're ready to do more strong induction stuff?
Yes.
Jacob, are you good? Okay. All righty. Okay, so in class on Friday, we talked about strong induction. Strong induction, you assume that like all the dominoes have fallen to a certain domino, and you use that assumption to make sure that you know the next domino can fall. We did this with postage. And maybe obvious example too is that like what scores could happen in football. Like it's not that interesting, but the only score you can't get, well, in anything involving it's just a single one, because you can move by twos or threes, and so you can get every even or odd number other than one. Also sevens and sixes, but that's, the fact that you can move by twos or threes means you can get everything, every number. This is a postage thing, but bigger than 12, you can get every one of them. I don't know what 4 or 5 cent postage is, so I don't really know that that's all that helpful. Anyway, so what we did here is that we assumed, we showed some base cases. We set this up where we go from 3 to no 4-cent stamps and none to 3 5-cent stamps. So we have like a whole cycle basically covered. And then for the inductive hypothesis, we assume that I is between 15 and K, 15 being the end of our base cases. And that is so that we can step back 3 so that we're adding on one of the things that we want. We could also step back 4 if we wanted to, so that we would be adding on 5, because we want to be able to write this as a multiple of either 4 or 5. So if this was a 2 and a 3, you would do K minus whatever. You're trying to get the thing you're adding on to be a multiple of one of the ones you have. Like if we were trying to say 2A plus 3B, you with me? Are you with me? If you were trying to do like 2A plus 3B, you would have K plus 1 is equal to K minus 2, I would do, plus 1 plus 2, right? So you've got this that's actually adding 0, but I've ended up adding on a multiple of 3, which is great. You could do K minus 1 there. Then you don't need strong induction, so that's fun. K minus 1 plus 1 plus 1. This is a plus 2, so it'll go with the A's there, right? So you're stepping back so that whatever you're adding on is a multiple of the thing that you want. Okay. Y'all are good? Yes? Great. Let us talk through recursive sequences. Okay, so recursively defined sequences, basically, I mean, we talked about the Fibonacci sequence already, and then I had some random example that doesn't make any sense, so I still haven't figured that out, but I will later. So these first 3 are not recursively defined. These are just sequences. A sub n is 1 over n. All you need to know is what n you're on. You plug it in straight up, and you have the like entry in the sequence. The sequences can also be defined recursively, where you need to know, look at how many S's are in terms, where you need to know, look, it's like the devil got in me while I was typing. You need to know, or Harry Potter, Parseltongue, I don't know. Anyway, focus. I told my husband yesterday that maybe I actually have ADHD, but I've just always had such high anxiety that the ADHD hasn't like revealed itself. But now my anxiety is being treated well by a psychiatrist, and so maybe the anxiety is being dealt with, but it's making the ADHD show. Do you think that could be a real thing? And he told me Would you please stop reading the internet? Thanks for your compassion, dear. What? I'm in my 30s. Maybe I have ADHD. I think my kid does.
Well, she's where I got it from. So.
Yeah. You have ADHD also? How do I help my kid? Huh? Is there any other than medicine? He's 6. I feel like it's too early for medicine. Is it not?
It's just the school system in general doesn't cater to, it just caters to one kind of teaching versus like actually hands-on. I feel like that's what ADHD, like my little sister, I'm pretty sure is ADHD.
Yeah.
So she's really good at doing stuff and doing it with her and slowly and hands-on. Like it's just taught to her straight up.
My son's issue is not learning. It is sitting still while learning, not making noises while learning. It's a distraction for others, not himself. He's learning, and in the process of learning, he's mobile and loud. So it's not that, like it's not an inattentiveness. He's paying attention. I guess there are different kinds of ADHD. But also like he knows everything that's happening in school right now, so he doesn't have to learn. So I think he's bored too, which is also not helpful. So anyway, we're going to the doctor tomorrow. Yeah, I don't think so. I'm not saying he's not a genius. He might be, but I don't think he would be cool. Right, and then you're just bored. Yeah. Well, I mean, like in an ideal world, everything could be individualized, right? But it can't be. I can't homeschool my kids. He might be here tomorrow. Yeah, I don't know. His teachers have done a really good job with him. I'm grateful for that. But yeah, I think he does better at school than he does at home. Because there's a lot more structure, I guess, for him to sort of, I don't know. I'm waiting for your thoughts.
I do better at college than I do at home than that. It's more focused at school.
Yeah. Yeah.
There's some professors who are kind of like, just here's the PowerPoint, and you just watch the PowerPoint, you'll be fine. It's like,
I'm sorry, no, I cannot do that.
That's not teaching.
No. Yes. I agree with that. Okay. Well, I'll keep pondering, but I'll keep you posted. Thank you for your openness with me and for listening to me. Sequences can also be defined recursively. So a sub n is given in terms of other things around it. So like the Fibonacci sequence we talked about, you get the next entry by adding the 2 previous ones. So you start with some like initial values. Let's go with that. You start with these initial values and then you use them to find the other terms. So, I mean, we've done this before, but f sub 2 would be f sub 1 plus f sub 0. So that's looking at 1 plus 0, which is 1. F sub 3 is going to be f sub 2 plus f sub 1. F sub 2 is 1 and f sub 1 is 1, so that is 2. F sub 4 is the 2 previous, so F3 and F2. F3 is 2. F2 is 1. I'm getting lost in all of the numbers, but here we are. And this goes on and on and on, right? But knowing the entry you're on, you need to know the 2 previous entries. So This makes sense why we're talking about this now, because you have to use strong induction to do these things because they're defined by more than one thing in front of it. And so like you have to know that the two things in front of it hold with the whatever the inductive hypothesis is, and then use them to say the next step holds too. Okay, so number 2 here, we have a sub 1 is 2, a sub n is a sub n minus 1 squared. So a sub 1 is 2, a sub 2 would be a sub 1 squared, which is 4. A sub 3 is going to be a sub 2 squared, so 4 squared, which is 16. A sub 4 is going to be a sub 3 squared. Is that 256? Great. I'm going to stop there because I don't know what 256 squared is. Are we doing okay? Do we understand what's going on? This one is defined in terms of only one previous entry. So if we were doing something with induction here, we could use regular induction. We wouldn't need strong induction because it only depends on the previous thing. So you need about like the K, and you can use that to prove K plus 1. But like number 3, number 3 is a lot of numbers. Number 3 depends on the two previous, so you would use strong induction on that one. I would really rather not do this, but that's all right. Y'all can see that I can't do any arithmetic in my brain, which is unfortunate in my line of work, but I have no idea what 5 times 17 is. I do know what 6 times 6 is. So. Y'all know this just in your brains? Oh, you did 15? What?
It's 100 minus 15. It's 5 times 3. Sorry.
What? 100 minus 50. You're telling me how you got to 85? That is, go through that again.
5 times 20.
Yeah.
And you have 5 times 17.
Then subtract.
That's 16 times 4. And then 5 times 20. Yeah.
They're doing a lot of number sense things.
Yeah, how did you do it?
How did you do it?
5 times 7 is 35. 3 plus 5 is 8.
I just did 17 times 10 is 170 divided by 2.
Nice. Emily, did you try to do it in your head?
I don't think I did.
No, I didn't either. I didn't either. What did you do? Yeah. Well, that's what Janiyah did. She just did it in her head, but she like carried the one, situation.
I counted all the way. 1, 2.
Yeah.
My son tried to do 40 times 10 yesterday. I was like, how do you do 40 times 10? He was like, 10, 20, 30. And I was like, no. And he said, 40, 80. And I was like, okay. Because he understood that, like, I can do this the other way. And, whatever. But I was like, okay, let's back up. Just because he was asking me how many years 40 decades would be. He just learned what a decade is, I guess. And now he says it all the time. And then yesterday asked me about centuries. Like, can we please, I don't want to be multiplying by, I don't want to do this. How did you get to 85? Y'all were telling me it's 85 minus 36. I didn't do that wrong. You're just shouting numbers at me. I got overwhelmed. Corey.
So we're the same way. I just did 5 times 10 is 50, 5 times 7 is 35. Just combine the two and get 80.
I am shook. All of you did that differently with good math reasoning. Emily, fine. I didn't do it in my head either. All of you guys did that differently and did it correctly. That's just weird. Isn't it wonderful how weird math is? That's why it's so good. And you should all at least have it as your minor. Or a major. This is 49? Great. Do I have to keep going on this one? Great. Okay. No, please don't. Spare us all, Dr. Thomas. Okay, the sequence here we have S sub n is defined by S sub 1 is 1, S sub 2 is 3, S sub n is S sub n minus 2 plus 2 times S sub n minus 1. Okay, so this is a recursively defined sequence. It depends on the two previous terms. That's why we start by being given 2. What we are going to do is prove that S sub n is odd for all n bigger than 1. Okay, so this is a part that really confuses students often. What part do we know, and what are we trying to show? What we know is how the sequence is defined. This is fact. What we're trying to show is that S sub n is 2k plus 1 for all n. Okay, right? So this is what we know. This is what we're trying to show. For the base case, we're going to do n equals 1, 2, and 3. So you're going to say it still works for these ones that are already defined. These are odd, obviously. And then you're going to figure out what S sub 3 would be and show that it is also odd. So when you do strong induction stuff, especially with sequences that are recursively defined, you often need to do multiple base cases so that you do it for the ones you are given and to establish the property. So like on, say, this one, I would still do 3 base cases, 1, 2, and 3. On this one, I would do 4. Yeah, show it for 1, 2, 3, and then 4. So, okay, let's go back up here. There is not a lot of space for this on here, so if you've got some spatial management issues, I would maybe do it in like 2 columns to make it very small. It's not enough space. Do you want to see mine? Where did I do this? This is also where I fell asleep while I was doing it, so don't worry about that. I came back here this morning and did just fine. Okay, so what we are going to do is we're going to say proof because we're starting to prove. And we're going to say let S sub n be the sequence defined by S sub 1 equals 1, S sub 2 equals 3, and S sub n equals S sub n minus 2 plus 2 times S sub n minus 1. We will use strong induction to show S sub n is odd for all n greater than or equal to 1. Oh. Okay, then I'm going to say for the base cases, I'm just going to go with a singular. Let n equal 1, 2, and 3. Notice S sub 1 is 1 and S sub 2 is 3, which are both odd. S sub 3 is equal to 1 plus 2 times 3, sorry. I'm plugging that into here. S sub 3 is S sub 1 plus 2S sub 2. So S sub 3 is 7. I'm going to put this as a capital letter, so. So, S sub 3 is 7, which is also odd. For the inductive hypothesis, assume for all I with 3 less than or equal to I less than or equal to K that S sub I is odd. That is S sub I equals 2K plus 1 for some, oh, don't use a K there, N. 2N plus 1 for some in Z. I can't use K because K is already used here. Okay, are we doing okay? Are we tracking so far? Okay, so in Z, we have S sub I is odd for some in Z. Okay, now what we're going to do is to consider S sub K plus 1. Right, so we, the base case, sorry, I'm going to write some scratch work somewhere. Base case N equals 1, 2, and 3. So we're looking at S sub 1, S sub 2, S sub 3. Inductive hypothesis, we let N equal K, up to N equal K maybe. So we're looking at S sub K is equal to S sub K minus 2 plus 2. I don't know if this is helpful. I forget why I was doing this. Oh, golly. Okay, so the thing that we want to show is that S sub K plus 1 is odd. Right, so base case, N equals whatever you're starting with. Inductive hypothesis, N equals K. Proof, you want to show that it works when N is K plus 1. Right, so in this case, that's a subscript. So we're looking at S sub K plus 1. We want to show that that's odd. Well, we're going to consider S sub K plus 1. What do we know that S sub K plus 1 equals?
Sub K minus 1 plus 2 S sub K.
Yeah, so we're doing that up here. So this is S sub K minus 1 plus 2S sub K. What do we know? Yeah, that these guys here are in here, right? They're both less than or equal to K. So we know that they are each odd. Did you say wait or right? Okay. So this is 2n plus 1 plus 2 times 2m plus 1. for M and N and Z, and that is by the inductive hypothesis, then this is 2N plus 1 plus 4M plus 2. And then rearranging that stuff, factoring out a 2 from the pieces that are divisible by 2, we're looking at 2 times N plus 2M plus 1 plus 1. So we would say something like, since M plus 2N, oh golly, those were the same letter I just said, N plus 2M plus 1 is an integer, S sub k plus 1 is odd. We have shown Sn is odd for all n greater than or equal to 1. Look how much space you used for your proof. It's so teeny tiny. I warned you about space, but it seems like you had plenty of space, Sherrod. Yeah, no, they would take forever. Yeah, and 5.7, you have to come up with the formulas too. You won't have to do that on the test. I don't think that's because if you can't come up with a formula, then you can't write a proof at all. These, yeah. So, I would think like one that's like this, and maybe one of another, like 2 regular induction, 2 strong induction is sort of what I'm thinking. But the 2 strong induction, like one would be a recursively defined sequence and one would not be. Yeah, yeah. Yeah. I don't know. I haven't written your test yet. That's a great thing I should probably do. Okay. Do you have questions about this one? All right. Number 2. We have this sequence A sub n defined by A sub 1 is 1, A sub 2 is 2, A sub n is 2 times A sub n minus 2 plus A sub n minus 1. This is what we know. What we are going to show is that A sub n is less than 2 to the n for all n bigger than or equal to 1. All right, so I'm going to write my proof. Sorry, Janaya. No scratch work to be found anywhere. Let A sub n be a sequence defined by, well, my. A sub 1 is 1, A sub 2 is 2, and A sub n is 2 times A sub n minus 2 plus, oh my goodness, A sub n minus 1. You ever do that thing where you talk sometimes and your words no longer make sense to your own ears? That's what's happening now. Like if you say piano too many times in a row, like, is that the word is? I'm not sure.
You and spelling something, like, I no longer remember if it's right.
No. I comes before E except after C.
Except science comes up.
Is right. And if it's something about neighbor and way, and then weekends and holidays, and all throughout May, I don't know. When does I actually come before E?
Just whatever they feel like.
Okay, so we have A sub n is a sequence defined by A sub 1 equals 1, A sub 2 is 2, A sub n is 2 times A sub n minus 2 plus A sub n minus 1. We are going to show by induction, strong induction, we will prove by strong induction that A sub n is less than or equal to 2 to the n for all n greater than or equal to 1. In proofs, it is so that your reader is on board with you, I think. Right? We are. Okay. We will prove by strong induction that a sub n is less than or equal to 2 to the n for all n greater than or equal to 1. For the base case, let n equal 1, 2, and 3. For n equals 1, clearly 1 is less than or equal to 2 to the first. For n equals 2, we have 2 less than or equal to 2 squared. Now a sub 3 is equal to 2 times 2. Nope, 2 times 1 plus 2. I want to use a whole line for equals 4. I'm not supposed to use my equal signs all horizontally. Can I do that? That's fine. That's fine. A sub 3 is 4. And 4 is less than or equal to 2 cubed. So the base cases hold. Assume for all I with 3 less than or equal to I less than or equal to k that what do I get to assume?
K minus 2.
Mm-mm,
K plus 1 minus 2.
mm-mm. What do I get to assume with the inductive hypothesis? It's an A, but whatever, we're with you. No, A sub I. Yeah. The inductive hypothesis, you're assuming this thing is true up to the kth spot. Right? Yes? Okay, so we assume for all I between 3 and k that A sub I is in fact less than or equal to 2 to the I. Remember, we're going to do the thing where we're going to consider A sub k plus 1. Now, Michael, you're ready. What do we know about A sub k plus 1? 2A k minus 1 plus A sub k. What do we know about A sub k minus 1 and A sub k? Actually, let's pause. What the heck are we actually trying to show? We want to show that A sub k plus 1 is less than or equal to 2 to the k plus 1. Yeah? Okay. We know, oh, don't use that color. That's confusing. Pink? Oh, those don't look very different, do they? Black. No. That A sub I is less than or equal to 2 to the I. 3 less than or equal to I, less than or equal to k. Okay, how are we going to use that stuff now? What else do you know? What do you know about a sub k minus 1? Yeah, sure is. Okay, so if both of those are in that, what do we know about a sub k minus 1? That's less than what? K minus 1 is the exponent there, yeah. So a sub I is less than or equal to 2 to the I. So a sub k minus 1 is less than or equal to 2 to the k minus 1. What about a sub k? It's less than or equal to what? 2 to the k. So inductive hypothesis says a sub k minus 1 is less than or equal to 2 to the k minus 1, and also a sub k is less than or equal to 2 to the k, so we replace that equality with an n equality. Okay, what is 2 times 2 to the k minus 1? This is a 1. When you multiply like bases, you add the exponents, so this would be 2 to the k. This is also 2 to the k. That's 2 copies of 2 to the k. And what is that? It is 2 to the k plus 1, which is the thing we were trying to show. Ta-da! Okay. Thus, a sub k plus 1 is less than or equal to 2 to the k plus 1, and we have shown a sub n is less than or equal to 2 to the n for all n greater than or equal to 1. Period box. What do we think? How are we doing? Good? Any questions? What if I give you a few minutes to think through this one? And then together, we will do it in a moment. guess Eunice is coming today. You think they're having a test? I guess I haven't heard any chalkboard.
I'd love to ask the same thing.
Maybe she's still taking that test. That seems too long.
I don't know, maybe she wanted to break after the exam.
Yeah, that's not really Eunice's style. You know I'm gonna make one of you narrate this for me, right? Corey, maybe we'll finally let you talk. Brian, is there tutoring that is done separately for chemistry than what you do? Like, is there a professor that leads a tutoring session?
Yes, they do that for general chemistry, 121 and 122.
And who leads that?
Dr. Walker and Dr. Albert.
And are those well attended?
I don't know. Never been to one of those. When I was actually in those classes, I think I had somebody else at the same time.
Right. How does it feel like you're doing? Good or not good? Decent. You're stuck. Stuck?
Slow progress.
Slow progress. Progress is progress.
As long as the derivative is possible.
That's right. Fine. Ugh, how do I write this with one sentence? Do we like the semicolons so I don't have to write a whole bunch of words? Nice.
I was wondering, so when I was working out in my mind, I was just doing, for n 1, 2, 3, 4, say like, C of n is 1, comma, 3, blah, blah, and then
Oh,
series is blah, blah, comma, 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 and then say those are less than for
each.
values respectively.
Yeah, that's fine.
Is it an exam? Yep, you're right.
It was an exam that went 15 minutes over time. Yeah. Should I have been beating on the board? Would that have helped? Yeah. How did it go? You think, well, a 15-minute test that went 15 minutes over that's not well, right? What is that? What percentage of time over is that? 40? 35? It's a 50-minute test that went 15 over. Yeah, that's what I'm trying to get y'all to tell me. You guys could do math in your head.
Yeah, because 50 times 2 is 100, so 13 times 2 is 30.
It's 30. It is straight up 30. Brian is right.
My grandfather got a degree in math before calculators were a thing, and he taught me a lot of stuff.
Yeah, a lot of quick math. That's good. Takes a lot of number sense. Eunice, we've been doing strong induction proofs with recursively defined sequences. We've only done like 2 proofs today. It's been a little slow going for me. Maybe for all of us, but what's really happening is that we're all understanding what we're doing. Yeah, so we're going to be in really good shape for the test on Friday, right?
Yeah.
Ideally. I thought you said I agree, and I was like, great. You didn't agree, though. Are you done with this one, or are you still stuck? Do you need help? Should I continue doing this proof or no? Yes, okay. So we have this sequence C sub n defined by C1 equals 1, C2 equals 1, C3 is 3, Cn is that. We're going to prove by strong induction that C sub n is less than or equal to 3 to the n for all n greater than or equal to 1. For the base case, consider n equal to 1, 2, 3, and 4. C1 is 1, 1 is less than or equal to 3 to the first, C2 is 1, 1 is less than or equal to 3 squared, C3 is 3, and 3 is less than or equal to 3 cubed. Cool. Now, C sub 4 is 1 plus 1 plus 3. So C sub 4 is 5. Clearly, 5 is less than or equal to 3 to the 4th. And thus, the base cases hold. Okay, so now we want to assume for all I with 4 less than or equal to I less than or equal to K that, what do we want to assume? That C sub I is less than or equal to 3 to the I. Still there. Ugh. Okay, so we are going to consider. Janiyah has gotten well and sick again in the time that you have been sick. And well again, right? Are you still sick? Yeah. She got sick, well, and you've still been sick. Yeah. Or your lack of vitamin C. I bet. To try to combat whatever is happening. Okay. Okay. Scurvy. Gotta eat some oranges. Just gnaw on them. Okay, so we are going to consider C sub k plus 1. And what do we know? Eunice, this is the part I was telling everybody that people get confused about what we know, what we're trying to show. This is the definition of the sequence. This is the thing we're trying to prove. So we know this. We're trying to show this. Okay, so what can we say about C sub k plus 1?
Sub k minus 3 plus sub k minus 2 plus sub k or c sub k minus 1.
All of those are going to be a plus 1 on what you did. Yes, because you would plug in k plus 1 minus 3, so this would be k minus 2 and k minus 1 and k. But right idea, you're just plugging in k plus 1 there instead of k. Yep. Yes. Yes. But do you have it now? Good. Okay. So we have C sub k plus 1 is that. And what do we know about each of those things? They are in our indexing piece, yes. So what do we know about each one of them? They're less than 3 to the whatever their exponent or whatever x is, right? Right. This is less than or equal to 3 to the k minus 2 plus 3 to the k minus 1 plus 3 to the k. Now, what would we actually like to show? Well, we would like to show that C sub k plus 1 is less than or equal to 3 to the k plus 1. Okay, how am I going to do that?
That is less than 3 to the k plus 3 to k plus 3 to k.
Why do we know? Why does Brian know that 3 to the k minus 2 is smaller than 3 to the k? Well, because k is bigger than 4, right? So 3 to the k is bigger than 3 to the, or 3 to the 4th is bigger than 3 to the 2nd.
So they all become 3k plus 3k. They're in that.
They all become that. They all become this because they're in there.
Yes.
We do this because we're trying to get here.
They basically simplify it.
Yeah. They don't simplify. We're making it up so that we can make this conclusion. Yes. So like this is from the problem. This is where you're going. These two steps are creativity to get to here. So to keep the math correct, you need to replace these with something that is still bigger than them, but bigger in a way that's helpful. Bigger in a way that's helpful is rewriting those as all as 3 to the k's.
Math people can dump in air.
Yeah, as long as it's still true, and it is.
Chemistry, they complain about thermodynamics and all that.
We don't have any thermodynamics here. The C sub k plus 1 is less than or equal to 3 to the k plus 1. We have shown by induction that C sub n is less than or equal to 3 to the n for all n greater than or equal to 1. How are we doing? Good? I don't really want to do number 4. Right. But this one you don't even need strong induction for. You can use regular induction. Give that a shot and then send it to me if you want me to look over it. How about that? Okay. Regular induction works because this is only defined with one thing in front of it. So assuming the kth will give you the k plus first. Yes.
On the test, will you tell us what to do?
Yes. Like strong induction or regular? Yeah, I'll tell you. I want to talk through like one of these just very quickly. And that's all we're going to do with 5.7 because I kind of hate this section. But might be useful to you at some point in your lives. So you might do this in Cal 2. I don't know. I did do this in Cal 2 where I looked at a sequence that was defined recursively and had to come up with a closed form for the sequence. So like where it isn't defined recursively. So you did this on your homework. I did this on your homework. You did this on your last homework. I gave you a sequence and you and you came up with the closed form of it. You did. It wasn't defined recursively, but you did take a sequence and you came up with the closed form of it. So we're going to do the same thing now, but it's defined recursively. So a sub 1 is 2. A sub 2 is a sub 1 plus 3. So that's 2 plus 3, which is 5. A sub 3 is a sub 2 plus 3. So you're looking at 5 plus 3, which is 8. A sub 4, when you feel like we've got enough to sort of talk about things, we can, is a sub 3 plus 3. So you're looking at 8 plus 3, which is 11. A sub 5 is a sub 4 plus 3. So you're looking at 11 plus 3. So that is 14. We would like to come up with a closed form. So come up with a way to write the sequence that is not defined recursively, but only depends on n. Eunice, what? It is 3n minus 1. Emily, I don't know what you said. I didn't actually hear you. Yes, but you got to start somewhere. That's the thing. You've got to be able. So yes, it is adding 3, and this is how it's defined recursively, and that's simple. However, since it depends on the previous term, if I was looking at the 100th term, I'd have to get all of them to get the 99th so that I could get the 100th, right? But when it's defined like this, all you do is plug in 100, and you know it's 299 or whatever. Well, you would be. We are not. So you would prove, so the claim would be that a sub n defined by a1 equals 2, a n equals a sub n minus 1 plus 3 can be written as a sub n equals 3n minus 1. Then you would do your proof with your base case. You would n equals 1 and 2 probably. So a1 is 2 and 3 times 1 minus 1 is 2. So you're good to go. A2 is, what's A2? 5? And 3 times 2 minus 1 is 5. base case is done. The inductive step, you would assume for some k greater than or equal to 1, that a sub k is equal to 3 times k minus 1. You are going to consider a sub k plus 1. Now, what do I know about a sub k plus 1? That it is this. So it is a sub k plus 3. But then a sub k is 3k minus 1. What am I supposed to be making this look like? That's good. That's good because that's what I did. So the grouping these and factoring out that 3, you get 3n minus 1. So your closed form works. You've shown by strong or by regular induction that the closed form works.
Just supposed to be on the exam? Or will-
So you might have to do this proof, but you wouldn't have to find it. Like, I'm not going to make you sit on a time test and come up with this. I would tell you. And then it follows all the ones we've done today, right? Where you're proving something about each term in the sequence, whether it's an equality or an inequality, it doesn't matter. You're still doing the same kind of thing. Okay? Okay. You guys rock. Have a great rest of your day. I will see you on Friday or beforehand. Tomorrow from 11 to 12:30, I will not be in my office because I'm proctoring somebody else's class. So if you're planning to come to my office, come at 10 to 11. I'll be there. And also 1:30 to 2. Okay. So long. Thank you, ma'am.
Are we going today?
No one is signed up, and I have texts to see. Nobody said anything, but I will let you know. I'll keep you posted. You too. Eunice, I like your hair.